So tonight's video is going to focus on what we call Hardy Weinberg equilibrium. This is a way to basically quantify evolution, to determine if evolution is occurring or not. So we're going to look at the basis behind it, as well as an example problem and what the parts of the equation mean. So the first thing that we need to keep in mind is that if evolution is occurring, then I'm going to have changes in allele frequencies. If evolution is happening, right, so if the population is changing, I'm going to start to get changes in allele frequencies. When things become, when that selection is taking place, when certain things are better suited than others, you're going to see that allele frequency change and shift. So Hardy Weinberg equilibrium is in place for a population that is not evolving. So a non-evolving population. So if the population is not evolving, then that means that the allele frequencies over time stay the same. They don't change. Okay? And so some things that would need to happen for that population to not evolve, you've got to get rid of everything that could cause change, which is all of these things here. All of those things could lead to change, and evolutionary change in particular, which could cause my allele frequencies to shift. So if my population is not evolving, then I need to keep those allele frequencies the same. And so to do that, I need to meet my 5 Hardy Weinberg conditions. I need to have a very large population size. A very large population size, meaning that I cannot have anything, I can't have any genetic drift occurring. I cannot have any bottleneck effect, any founder effect. I need to keep my population nice and large, without any genetic drift. Small populations are going to become more susceptible to environmental changes. And so when I have a large population size, they are less affected by environmental changes because I have such, especially if they have variety, because I have such a wide variety of organisms there. The second condition is that I cannot have any migration. There can be no gene flow at all, no gene flow in or out of the population. So in the last example, we saw like the deer moving through. When we were talking about gene flow, we saw the deer moving through the pass in the mountains. That could not occur because that would change, that could cause change in the allele frequency. So you'd have to keep migration not happening, so that there was no gene flow in or out. You can't have any mutations. Usually when you say that one, that throws up a red flag to people, because how in that world would you control that there is no mutation? And you wouldn't. But this is a hypothetical situation. So no mutation, no genetic change, because that would change allele frequencies. You have to have random mating, meaning there is no sexual selection. So with random mating, there's no preference for a mate, not looking for a mate with the best feathers or the best dance or the best musical song or, that brings the best food. Random mating, and there's no selection, because if there's any kind of selection, that's going to change allele frequencies. So leading up to that, then you can't have any natural selection. Everybody needs to be equally fit to the environment. And so that there is no natural selection, because that's going to change allele frequencies. So these are hypothetical. Okay? These conditions are not usually met in nature. Okay? They're, like I said, the mutation thing in general makes it almost impossible for these conditions to be met. Okay? But they do provide a good null hypothesis. Remember, our null hypothesis is that there's no effect. Right? So if I'm trying to see if a population is evolving, then if my null hypothesis states that my allele frequencies are the same, or that it's in Hardy Weinberg equilibrium, okay, that means there's no effect, there's no evolution, nothing's changing. Okay? And I could test that. I can calculate it, and I can see if they remain the same generation to generation. So we can calculate Hardy Weinberg equilibrium by using allele frequencies in a population. Okay? We can find allele frequencies from genotype frequencies. We can use allele frequencies to determine genotype frequencies. Okay? We could, if we knew the whole population, we could count alleles. right? Assuming that each trait has two alleles, one dominant, one recessive. Okay? These are the things that you need to make sure you remember. You need to know what your equation stands for. We have two equations that we use, P plus Q equals 1, and then you'll see the other one in just a second. So we need to know what the P's and the Q's stand for. That's how it is on your formula chart. That's how you're expected to show work and write about it. So we need to know what the P's and Q's are. So the P is the frequency of our dominant allele. So really that just means how often does that dominant allele show up. And the Q is the frequency of the recessive allele. So P is dominant and Q is recessive. And they're going to add up to 1, right? Because 100% of our genes are either going to be recessive or dominant. If we look at this generation 1 right here, and we were just counting alleles. So this generation has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It has 14 organisms in it. So that means there are 28 alleles for this A gene. Okay, and for big A, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I have 14 big A's, which means when I count, I should have 14 little a's. Okay, and what you can see happening over time is in generation 10, I have 1, 2, 3, 4, 5, 6 big A's. I'm assuming again out of 28. Okay, so my allele frequency has changed. So that would tell me that population, so the allele frequency in the first generation was 14 over 28, so that is 0.5. In generation 10 here, it's 6 over 28, which does not equal 0.5. So we could say then that population is evolving. It is not in Hardy Weinberg equilibrium. We can also look at individuals, and we can look at phenotype to help us determine genotype. So we have another equation, P squared plus 2PQ plus Q squared equals 1. Okay, and I covered up that 2 there. So these are genotype frequencies. Okay, P squared is homozygous dominant, so that represents big A, big A. Q squared is homozygous recessive, so little a, little a. 2PQ is heterozygous or hybrid, big A, little a. One of the things I tell people to help them hopefully remember what stands for what is all of our things that stand for a genotype have the number 2, right? They're either a squared or they're multiplied by 2, but they all have the number 2. And genotypes have 2 alleles. So the P squares, the Q squares, and the 2PQ, that's when I'm dealing with genotypes. P and Q, I'm dealing with just the allele. Okay? So if I look at the diagram over to the side, you can kind of see where some of this comes from. Right, if I have a cross of 2 heterozygotes here, okay, my P squared is big A times big A, right? So P squared would be 0.6 times 0.6. Okay, my heterozygous is my big A frequency, which is 0.6, and my little a frequency, which is 0.4. Okay, and so I can use that to calculate the frequency of the genotypes. I can use these equations between the two equations and working back and forth and picking apart, this is what I know, okay, versus this is what I'm looking for. We can solve any of these Hardy Weinberg problems. Okay, there is nothing difficult about the Hardy Weinberg problems if you can get straight that the squares and the 2's, everything with a 2 is a genotype, and then P is allele and P is dominant allele and Q is the recessive allele. If you always start with your recessive, okay, so start with recessive information. No matter what you're looking for, you may have to find 4 things before you can get to the one that you want. But if you always start with the recessive information, you will be able to work these problems. We're going to do one quick example. We'll do some more examples in class and give you some time to work some longer word problems. Basically what these become are algebra word problems. So we're going to give you some time to practice some of them in class before we continue on with that virtual lab. So let's look at this example that we have here. So this example is really short and simple here. It's not even in a word problem or anything. It tells you your population. It tells you you have 100 cats. And it tells you that 84 are black and 16 are white. Okay? And it wants to know how many of each genotype, assuming it's in Hardy Weinberg equilibrium. So all I know is that I have 84 black and 16 white. So based on this, I would assume, right, that white is recessive. So that tells me that these cats are little a. And it tells me that these cats that are black are either big A, or big A, little a. And if I think back to my equation, little a is equal to Q squared. Big A is P squared, and big A, little a is 2PQ. So based on this information, okay, I can choose to either work with this recessive information over here, or I can choose to work with this looking dominant information. Okay, well, the recessive information only has one variable, the Q. The dominant information, I'm taking into account both P's and Q's. And that becomes significantly more difficult to solve, especially if I don't know one of those two things, if both of those are unknown to me right now. So if I want to know how often this recessive genotype shows up, then I can just say 16 out of 100. So I can say that is going to be 0.16, and that's equal to Q squared. So now I have a value for Q squared. So if I know Q squared, now I can take the square root of that, and I can find Q. So now I know the frequency of the homozygous recessive genotype is 0.16, right? And I know the frequency of the recessive allele is 0.4. The question asked me how many of each genotype, assuming Hardy Weinberg. So I haven't even answered the question yet. I have found frequency, but I haven't found how many of each genotype. Well, I can go ahead and I know that little a, there's going to be 16. They're the only ones that looked white. But now I need to find out what P squared is and what 2PQ are, and I can apply that to my population to find out how many of each genotype. I got the 16 because my population is 100, right? 0.16 times 100 gives me 16. So if I use that other equation, P plus Q equals 1, I can just solve for P, right? P plus 0.4 equals 1, so P equals 0.6. So now I know the frequency of the dominant allele. Okay, so the frequency of the dominant allele is 0.6. So if I want the frequency of the homozygous dominant genotype, that is 0.6 squared, which is equal to P squared. And so 0.6 squared is 0.36 is equal to P squared. So answering my actual question of the homozygous dominant genotype, there are 36. So out of that 84, 36 of them are going to be homozygous dominant. And now I can just plug in information, right? I have P and I have Q. So 2PQ, which is my heterozygous genotype, 2 times 0.6, not 0.36, because it's 2 times P, not P squared, 0.6, 0.4 equals 0.48. So I know then for the heterozygous genotype, there are 48 cats. And I can check this using my P squared plus 2PQ plus Q squared equals 1 equation. When I add those up, when I add up all those frequencies, they should add up to 1. So you'll notice I didn't really use this equation. You are not going, as a general rule, you are never going to plug stuff in to this more complicated equation here. That equation is for you to check work when you're done. But you'll never really plug anything into it. You'll plug things in more to this P plus Q equals 1 equation, and then you'll just calculate p squared and then 2pq. Okay? But very, very rarely will you plug something into that bigger, longer, complicated equation there. Okay? So we'll look at some more examples of this. So what is key when you are doing these problems, again, is you need to know what the symbols stand for. P squared, 2pq, q squared, p and q. You need to start always with recessive. Always start with recessive, and you need to annotate what it's asking you for. Does it want a frequency? Does it want a percent? Does it want genotype? Does it want allele? Does it want phenotype? Okay, so you need to always make note to make sure that you actually get to what it actually is that they want to know. So we'll practice with these in class.